Students' Evening Hymn. Now, no more the slanting rays with the mountain summits dally. Now, no more in crimson blaze, evening's fleecy cloudless rally. Soon shall night front off the valley, sweep that bright yet earthly haze, and the stars, most musically, move in endless rounds of praise. While the world is growing dim and the sun is slowly descending past the far horizon's rim, earth's low sky to heaven extending, let my feeble earth notes blending with the songs of cherubim through the same expanse ascending, thus renew my evening hymn. Thou that fillst our waiting eyes with the food of contemplation, setting in thy darkened skies signs of infinite creation, grant to nightly meditation what the toilsome day denies. Teach me in this earthly station heavenly truth to realize. Give me wisdom so to see these brief hours of thoughtful leisure, that I may no instant lose in mere meditative pleasure, but with strictest justice measure all the ends my life pursues, lies to crush and truth to treasure, wrongs to shun and right to choose. That when unexpected sleep over my long closed eyelids stealing opens up that lower deep where existence has no feeling, may sweet calm my languor healing, lend no strength at dawn to reap all that shadows world concealing for the bold inquirer keep. Through the creatures thou hast made, show the brightness of thy glory, be eternal truths displayed in their substance transitory, until green earth and ocean hoary, massy rock and tender blade, tell the same unending story, we are truth in form arrayed. When to study I retire, and from books of ancient sages glean fresh sparks of buried fire, lurking in their ample pages, while the task my mind engages, let old words new truths inspire, truth that to all after ages prompt the thoughts that never tire. Yet, if led by shadows fair, I have uttered words of folly, let the kind absorbing air stifle every sound unholy. So when saints with angels slowly join heaven's unceasing prayer, mine as certainly, though slowly, may ascend and mingle there. And there is more, if you can even believe it.
I think that's awesome.
Going to stop there. I am going to stop there because I had started reading this. I did not quite realize the extensive number of. I saw how short the lines are for each poem, for each line in the poem, but I didn't realize how long it was. Well,
it's pretty good, actually.
It is, and it was the disembodied voice in the background, whom you will soon see.
But what is this? What are we doing?
Gosh, what is this? All right, you're watching SG2 on Space, the only weekly space show. Go to www.youtube.com/streams. The disembodied voice in the background. If I'm going to bring him up, here we go. There, got it. You. There, see? All right. Leonard, how are you doing? Can't hear you. Unless
there. I'm good.
Okay.
I'm good, Shen. I had to I have a little mute button. It turns pink.
Sounds good. So as you were saying, that was a decent poem. That was by James Clerk Maxwell. Let me continue with that. It's called A Student's Evening Hymn. And
James Clerk Maxwell.
Yes. So this if you want to find his poetry, you can go here and obviously he's long dead. We're going to talk about some of the history behind his work today, as well as just overall the Maxwell equations.
He was kind of an amateur poet. He that wasn't his job.
No, but what's interesting is that he's written a good chunk. I mean, at least.
And it's not too shabby.
Yeah, it's not. One of them that I thought of reading was called A Problem in Dynamics, which has some math equations, but like I think I've read that one before, so decided to go with that other one, which was not bad.
He was an engineer. He was a scientist. He was a
Yeah,
physicist.
imagine that. I mean, it's
Yeah.
kind of familiar. But before we go on with the show, I do have to say, okay, so you're watching SG2 on Space, as noted. Another thing you can find us is you can go to youtube.com/eshinga/podcast. And also recently started as well the, what do you call it, Spotify podcasters. So podcasters at spotify.com, or just go on Spotify and you can look up SG2 on Space. Those audio episodes are not going to be live. So if you're listening to that on there, we're not, you're obviously not seeing our faces, and it's not live, but hey, it's audio. So what do it is what it is. Make sure you can support the show on patreon.com/SG2 on Space. And thank you for the patrons, Kyle Baker and Sam Welsh. And thank you to my producer for 2 years, Atum Ra. So you can support the show on patreon.com/SG2 on Space. This is episode 177, which I cannot even believe, but that's how long we've been doing this. And we're going to talk about Maxwell equations. So let me just throw this at you, Leonard. What is this guy? I mean, who is he? I mean, you say he's a
Maxwell.
Yeah, why not?
Well, have you ever heard of Einstein?
Yes.
You've heard of Newton, Isaac Newton?
Yes.
Yeah. Well, those guys. Those were two famous scientists. Maxwell is right up there with them, although he's not as well known, for whatever reason. So in the late 18th century and early 19th through the mid 19th century, people were playing around with electricity and magnetism, and there seemed to be some kind of connection between them. So if you've heard about Faraday's Law, if you learned about that, and then Faraday,
yes, definitely,
he was in the early 1800s, and he discovered that if you move a magnet near a wire, it'll induce a current. So if you wiggle a magnet around a wire, then electric current will flow in the wire. But it was not, and he had some fairly coherent laws associated with that rate of change of the electric flux through, or the magnetic flux through a loop of current and so forth. And then there was also Ampere. And Ampere was a contemporary, and he discovered that currents in wires that did the opposite, that did the other thing. If you have a current flowing through a wire,
like Ampere's law, right?
Yeah, so you get Ampere's law, and so James Maxwell, people were coming to the conclusion that electricity and magnetism had something to do with each other, right? And what he did was he played around with the equations, and or with some equations with a physical theory, and produced 4 equations that relate the variation, the time rate of change of magnetic field, electric field, to sources, which are like electric current and electrical charge. And so and we call these the Maxwell equations. That's what he did. And so
how did he come up with it? Did he just recognize that somehow?
Well, he wrote a paper in 1861, and I have the paper somewhere, and he talks about just trying to. He was good at math, right? And so he was able to come up with various equations that would relate to these parameters. So one of the things that he predicted was that electricity and magnetism together make up electromagnetic radiation, so that waves will propagate in space.
I mean, that's basically what we call light, right?
Light and radio waves, microwaves, gamma radiation, and so forth. These are all electromagnetic waves, and they they are a recognition of the unity of magnetism and electricity. And so it's a great achievement. Magnetism had been known for centuries. People thousands of years ago knew about magnets, and it was probably like an awesome thing. It's like
I
you
mean,
can,
it's still
yeah.
an awesome thing.
Uh,
But I suppose just for most of history, we never put even when we discovered electricity, we did not see any relationship between those, right?
I think that's true up until the 18th century, when people were noticing and observing these things. So I think that's true. That up until the late 18th century, did when people started to realize that electricity and magnetism had something to do with each other, and Maxwell was able to unify the two physical fields into a single, kind of like he sort of unified them. And that's sort of the name of the game with physics now, is like
Unification,
attempting to unify all the fields together. And today we have the standard model
which is
of
incomplete from what I understand.
so it doesn't it's self-consistent. I mean, they
Hmm.
discovered they were able to demonstrate the Higgs boson about 10 years ago, and with spent spent tremendous amounts of money building the Large Hadron Collider, and now I'm afraid that they're searching for things to do with it, since
Yeah, the
right. But we can talk
I,
about that another day.
right.
um,
I want to go back to talking about these particular equations.
okay,
So if we can, let me see if I can bring this
if you
up
can get up there, I can tell you
here.
all about them.
Yeah, tell me about Gauss's law for magnetism, Faraday's law, and Ampere. Well, you already
Okay.
mentioned like a few of
All
them.
right.
So
So these are what are called the differential form. So these are all related to um, uh, the they can also be expressed in a different form, but this is usually how you see them. And well, you have to hold that still there,
okay,
Ken.
fine. I will hold
So
it still. I was
so
saying,
Gauss's
go
see
ahead.
okay, the first one is Gauss's law, and the the parameter, the value on the right hand side is charge density. So that the electrical charge density, and that epsilon underneath is it's just a conversion factor. It's called the permittivity. um, uh,
Permittivity constant.
Permittivity. Usually we see epsilon with a little naught underneath it, a little zero, to show that it's the permittivity of free space. And then on the left hand side, that's a symbol that says that there's this thing called an electric field. Electric field is sort of proportional to the force that a charge would feel, if it was subjected to that electric field. And so the funny symbol there means that it's like the divergence of the field. So
Hmm.
the field kind of like, if you think of an electric charge, and so then you have like lines of electric field coming out of it. So
Yeah.
that's what that expresses in a mathematical form. Um, so that's a what they call the
Del dot
divergence.
E equals rho v, rho sub v over epsilon. So the divergence of the electric field is equal to
To the charge density,
to the
right?
charge density divided by the permittivity.
Yes, right.
Um, and so okay, and
And then the next one, and so that's an observational law, and that's called Gauss's law because maybe some of our audience is more familiar with it in high school physics, where you have Gauss's law, where you have a Gaussian surface. You have a surface, and all of the lines of the electric field are sort of piercing the surface, and that's an exact measure of the amount of charge that's contained within that surface. So these can be. We're not going to do math here, but I mean
yeah,
that's the
yeah,
you
yeah.
know
I mean, doing math is much more
yeah,
fun when you're
but
sitting by yourself in your room, I guess.
uh
Cool.
yeah, very very lonely people. A
I
lot of,
mean,
a lot of
that's what you have to do in order to come up with these.
So
Um,
the next one there is so H is the symbol for magnetic field. Sometimes we use B for magnetic field, and but this is I guess they call it the magnetic displacement sometimes. Um, but anyway, it's a physical principle that there is no magnetic charge.
What does that mean?
Well, um, there's an electric charge, so that means that people know what that is. It's like
There's
it's a
positive and there's negative.
there's a positive and negative electric charge.
Electric charge.
Okay, and so
Right.
all of the
So
charges that are emanating from a positive charge end up on a negative charge somewhere, right? So
mhm.
the little arrows that are represented by the E vector, that E,
Yeah.
that capital E. So that's a field that permeates all of space. And if you have if you have an electric charge, then the the
The
the
yeah, definitely.
the ends of the arrows are emanating. They're coming out of the charge. And then if you have a negative charge, they end up
For
they
instance, your headphones right now, there's electricity flowing through it, right?
electricity flowing through your body. That's
And there's electricity flowing through your body. I mean,
yep.
we're generating electric fields too, but electromagnetic fields. But okay, continue on.
I
So
was going to say about
magnetism.
the magnetic displacement there, the magnetic field. So it is a principle of physics that there is no magnetic charge. There is no. Sometimes you'll see monopole. You can Google the word monopole or magnetic monopole,
Mhm.
right? Well, there is none. It is a principle of physics. It's an observational principle that the divergence of the magnetic field is zero everywhere in the universe. And so that's what this
This says there is no such thing as a monopole.
there's no such thing as a monopole.
So whereas in electricity you could have positive charge or
You can
just
have positive
negative.
charge or negative charge, and there's
But
no magnetic current. There's no magnetic, there's no analog to a magnetic current.
understood.
There,
So
there,
if I have a magnet and it has like a north and a south pole, right?
yeah,
So you're never going to have one that just has a north pole.
that's right.
Okay.
Although I want to put a caveat on that. I remember in graduate school when I was taking this class, the professor pointed out that there is a way of manipulating the units for electricity and magnetism so that you
Mhm.
generate a sort of artificial magnetic pole. And so I always thought that was interesting, but I never pursued it any further. That there is a way of transforming these equations so that there's a kind of a mathematical um, monopole. But that I just wanted to mention that. So the third equation is that other symbol with the cross there, where you go that the that symbol is called a del operator, and it's represents the some calculus,
Some
spatial
calculus stuff.
some spatial gradients, right? And the cross means curl. So the curl has something to do with like something that's circulating around,
Yeah.
right? So it's the degree that the electric field is circulating around, making a circuit. And so people know that when Faraday showed that when you have a magnet, a permanent magnet, and it approaches a a wire loop, that it will induce a current that rotates around the loop. And so that's an expression of how that happens.
Okay. So you're saying if I have a wire, let's just say, and there's current,
Hmm.
there's electrons flowing through it, and I put something else next to it, you're saying even though those things are not touching each other, this wire with electrons flowing through it, it has a current, obviously that's
Yeah.
flowing, will
Uh-huh.
create will induce a magnetic field, right?
Yes.
Create a
Well,
magnetic field.
that's the fourth equation.
Oh, that's the fourth
Yeah.
equation. I said it backwards then.
Yeah.
So what is this one? What is Faraday's thing? Is that
This is that a changing magnetic field will induce a current in a loop
okay,
of
the
wire,
other way. Okay.
right?
If I take a magnet and I start moving it around, it's
Yeah.
going to generate electric field.
And the
Okay.
moving around, that symbol on the right hand side with the little like looks like a delta over a delta t thing.
Right.
That's the derivative. That's the time derivative of the magnetic field. And that constant there in front of it is called mu, right? So and
Right.
actually it's called the permeability, and it's a proportionality constant that's sort of empiric. Yeah,
This is how one way we generate electricity, right?
That's how we generate. Yes, that's exactly how we generate
That's exactly how we
electricity.
generate electricity,
Yes.
where we
So,
take
so
a
yeah, yeah. Physicists actually don't know how to generate electricity. They just know how to tell the engineers what to do, and then the engineers will go and they'll wind the coils and they'll shape them and do all kinds of experimental things and
right.
calculations to actually make it work. So
But I think the point of it is that you move like
you move
a
a magnet
you
near a
move a
coil of wire, and you'll
and
induce a current in the
you
wire.
generate electricity.
You
And
generate,
the other
yeah.
one, Ampere's law, do the opposite, right? You take
Yeah, and so that last equation, it does the same thing for magnetic field. So H is the magnetic field, and if you have an electric field that's changing, okay, and
changing
how would you
electric
do that?
field
Well, you could take a electric charge and move it, in space, and then a magnetic field will be generated.
generating.
Or you can have an electric current, and that's what that J is. J is
Right,
electric current density, charge density. So everybody knows what that is. It's like amps, like
right.
number of, and in this
Amp
case, the
per
units
meter.
here are amps per square area,
Yeah, right. That's how
right?
much current is flowing through the
Right.
wire. Okay.
So,
So
and so so there you see how they're kind of symmetrical, and the curl of the magnetic field is proportional to the electric current that's flowing through it, and then also any changing electric field. Now, okay, so we're and actually you see that permittivity constant also show up again. You see the epsilon. That's the Greek letter epsilon.
right.
So I was going to say the Greek letter epsilon is called permittivity, and the Greek letter mu is called permeability.
Permeability. What are
And
those
these are
constants?
physical constants that are a property of free space.
Let me
We
click on it.
we don't we don't invent them. They
This
are
is
they are
permittivity.
it happens that the units have been set up so that the permeability comes out kind of clean. But
Oh,
there it is. That's the
that's permittivity though.
that's
This one's permit.
permittivity. The permeability actually is simpler, but here's the thing. Okay, don't
It's fine. I
expose any.
won't move it.
Yeah,
I won't move
I don't want to give away the big climax of all of this. Is that
this.
okay? When you combine those two equations, the ones that have the curl there and get away, and you don't have any
Yeah.
electric current, you'll get an equation that will describe a propagating wave in space. Okay,
You take the last two equations of
yeah,
Faradays.
put them back up there. So scroll back down, and so
Oops, one moment.
uh-oh,
Where did it go?
I
Oh,
don't
I
know.
can't find it.
You can't
Oh,
scroll
wait.
anymore.
No, I can't. Where is
Maybe
gonna go
maybe
back? Ah,
you
is this
can't do
working?
that.
Hold on.
Okay, I'm holding.
I mean, I don't know why I'm telling you to hold on.
So, well, I mean,
I don't know. Backspace.
there you
didn't
go.
work, so
There you go.
here,
Backspace didn't work, but whatever you did work. All right.
Well,
So
I
those,
mouse
so
button.
the third equation and the fourth equation, there's a way that you can combine those two together.
Well, you just plug it in, right?
Yeah.
You del cross H. I mean, you can manipulate that, so you can do the I guess the partial derivative with respect to time with H.
Then you get the magnetic field declining and the electric field increasing, and they're at right angles to each other, and so they will propagate as a wave that's propagating out into space. And you know what the speed there? Okay, here they are again, and they're using slightly different symbols.
This is using the same thing, slightly different symbols.
Yeah.
And the speed is what?
So the speed of that wave is equal to 1 over the square root of mu times epsilon.
Wow. What is that?
It's well, mu is the permittivity, and I mean mu is the permeability, and epsilon is the permittivity. If the product of those two, square root 1 over the inverse of 1 over the square root of those two is the speed that wave propagates. And Maxwell discovered that. He knew that, and actually it's a speed that has been well observed. It's the speed of light.
Is this it? The scalar wave equation?
Yeah.
Or am I not getting this?
And yeah, that's it. Yeah, you got it. And then there it is. You see the square root. You see there at the bottom the speed that this wave propagates, and it's just a property of the equations. It's not a property, and it's a property of space, is the speed of light. So the speed of light, and so people were wondering, this is very revolutionary, because here's these two static measurements. These you can measure the permittivity and the permeability from just static measurements. You don't need to measure the speed of light or anything, but you measure these two things and you combine them into this wave equation, and you get a number that equals the speed of light. And they knew this in the 19th century, and so it's like so this was pretty exciting. Einstein was looking at these equations, right? And so what they noticed is that these don't transform when you, no matter how fast you're going. So one of
Hmm.
the principles of
Special
special
relativity.
relativity is that the speed of light is just a constant, and it doesn't
Right.
matter how fast you're going. Like,
Yeah,
so
it's pretty
it's like
remarkable.
you can't catch up with the speed of light, because it'll always seem to be propagating away from you. And this is, and Maxwell didn't recognize that. I think that they were wondering about that at the time, but that this is kind of a cool demonstration. One of the reasons I wanted to bring this up was um, that these are static measurements. These are things that you can measure in the laboratory. You don't need any, like really exotic. Um, you just need, an ammeter and something to measure force and so forth, and those kind of things. And
So,
you can
so go
and
on.
and then you can back out what the permeability is, and you can back out what the permittivity is, and the product of those two is the speed of light. I mean, the product as shown in the figure there, or in that
1 over the
equation.
square root of mu
Yeah,
times epsilon is equal to c, the speed of
right.
light.
And it doesn't matter how fast you're going. It's always going to be
Electric
the
and
same.
magnetic fields in free space, a region without charges or currents like air, can travel with any shape and will propagate at a single speed
Yeah.
called c. This is an amazing discovery and one of the nicest
It
properties
it
I think.
is an amazing discovery, and Einstein used this. He was pondering this, and a lot of people think that Einstein was, looking at, the the interferometer measurements from
Right.
Case Western. I forgot who they were. The 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 interferometer measurements of the ether drift. People thought that there was like that the space had an ether, some kind of fluid that would vibrate, and he said that he was not thinking about that. He was thinking about the Maxwell equations, and it's like no matter how fast I'm going, in whatever frame I'm in, the speed of light is still escaping me at the same speed. And so it's weird.
That is really weird.
Yeah. So, and
Hey, I remember learning these
yeah.
formulations. That's an integral form, I suppose, but it's
Yes,
same
yeah,
thing.
and yeah, so you learn this in, like, people learn it in high school, I guess, and also in first year college physics, and it's fun, and people should study this and have as much fun with this, and be amazed as much as I am. So
Um, so so for Maxwell, he like it seems like these four equations were already known, right? He just
no,
like uh,
he put them together in his
in that particular
in that
formulation.
paper, that 1861 paper.
Okay.
And like uh, uh, 500 years from now, if people are still around, and our robot overlords have not taken us and extinguished
Um,
us,
I mean, yeah,
but
there's always that possibility,
so
right?
that, when people look back at the 19th century, and as far as physics is concerned, this is the highlight of the 19th century
Okay.
in physics.
Do you know much about what is it, the quantum electrodynamics?
Well, do I know much about it? Well, that's
Well,
what.
I was just saying, like the quantum version of Maxwell's equations, I suppose, would be quantum electrodynamics, right?
Well, so that's Feynman's work. We
Right.
we can talk about that another day.
We definitely
But
can. But okay, go on. Sorry.
that's all I wanted to say. I wanted to get to the speed of light from static measurements in the laboratory, and it's cool.
Okay.
The end.
Oh, I realized my. Okay, so
Now we could talk about something else if you like
um,
your favorite
what,
topic.
why would that be my favorite topic?
No, I don't. You usually have something else you want to talk about.
Okay, let's talk about it. Actually, before we talk about it, here, let me.
Well, you know, Maxwell was a Scotsman. He was Scottish, and like, you know, so, and you know, Scotland has a lot of like reputation for producing engineers and people with this kind of background.
I want to
So
show this. This is what we're talking about, right? This is how light is.
that's what we're talking about. Yeah, and
So what is happening here?
well, well, you know, I don't know which is which. It doesn't matter. The blue is probably the magnetic field, and the red is the
Yes.
electric field. And you see, there's this interchange of the changing electric field gives rise to a magnetic field at right angles, and vice versa. And so when the magnetic field you know, changes, it creates electric field. And so
And
and
then
literally the energy of this wave actually um uh sloshes back and forth between magnetic and electric, and
right.
when this wave impinges on something, the electric field actually does the work as far as accelerating charged particles like electrons, usually electrons in an object, and so that's what gives things color, or what induces what creates a reflection in a mirror.
Yep.
The electric field will excite electrons, and they will re-radiate in the opposite direction. So there's a whole lot of
So wait, so
interesting
every
stuff going
time
on.
I see myself like when I look at myself in the mirror, that's what's happening. Like
That's
some
that's
light
what's
source is
happening.
hitting it, whether the light source is from the sun or a
Well,
lamp.
the light is reflecting off of you, and then it goes to the mirror, and the mirror is you know, it's very flat and coherent.
Oh, yeah,
So
yeah, it has to bounce off of me first, and then it
yeah,
hits the mirror.
and then it
Right,
goes into your eye and excites
and then I see myself.
yeah, and then you
Okay.
can see yourself. And not only that, but a lot of people don't know this, but when the electron is accelerated, it imparts a little velocity to it, and the velocity of the electron. Now we're talking about when the wave comes in, and the electric field from that wave, that's the red lines there, that will accelerate, let's say, an electron. Usually it's an electron. It'll accelerate it, so it imparts a little velocity to it in the mirror or in the object. And
Hmm.
then that velocity then has what's called a Lorentz force interaction with the magnetic field, and it tends to cause it to bend, you know, toward or away from the motion. And so the light can actually impart momentum to an object. So it actually has a little bit of pressure. And some people, I guess we talked about photon pressure a long time
We
ago in
did. We
space.
talked about solar cells and stuff.
And
So
so that's
yeah,
how that happens, is that it's the electron's motion that's excited by the electric field interacting with
right.
with the radiation's magnetic field that causes it to impart.
This can you explain how we're talking about electromagnetic waves here, but what about I thought those like light particles are like photons, right? So is
Well,
that just a different interpretation?
so the interesting thing about all of that is that so that gets into quantum, you know, quantum mechanics. And so when you turn the power down, when
Right.
you know, so you keep decreasing and decreasing the power until you just have little pieces of light, and we call those photons. So one of the things that was observed was that um, for example, in a photographic film, you'll have like little pixels or little,
Hmm.
I forgot what they're called, little domains of dye that are the chemical. And so you'll have a little piece that will get excited. So that happens in a quantized, that becomes quantized, meaning you can only, you can shine a light,
Hmm.
and as far from Maxwell's point of view in 19th century, it was all a continuous theory. So you could just turn the power down, turn it
Right.
up. But
Okay.
it turns out that if you get down low enough, then you will only have one little particle of light. Then the light starts to behave like a particle.
Which this theory does not capture.
This is not that theory. It doesn't capture that
Right.
theory.
And then hence why we the whole realm of quantum
But
mechanics and quantum electrodynamics.
but the electric field is the wave function for the photon. So you remember we've talked about the wave function. So that is the sort of like the probability amplitude. So Maxwell actually observed a wave function, like the quantum mechanical wave. That this is the quantum mechanical, or this is analogous or proportional to the probability amplitude of the photon.
I ought to read up on that. I'm not too familiar, but I imagine
So yeah,
you have
so
to.
Maxwell was one of the he kind of plowed the ground for Einstein and then later for Planck and the quantum mechanic people. So Heisenberg, etc.
So
So
is this like the I don't know what kind of formula?
his paper is kind of neat because you need to use
Ooh,
complex arithmetic, and the notation is not quite mature, and so he is taught. You can see in the paper where he's talking about the square root of a negative number, and also there's this other theory having to do with the solution to what's called the Laplace equation, and and he had a number of solutions to that.
What was his original paper called?
Gosh, I don't know, but I'm pretty sure it was 1861. I've actually referenced it. I've looked at it.
The modern form of the equations in their most common formulations credited to Oliver Heaviside. So his original formulation was archaic, but
Yeah, his original formulation is awkward. Okay, but it's not that awkward. It's not that bad,
right.
So yeah.
Yeah.
And Heaviside is famous for the Heaviside function.
The second great unification in physics, apparently. What was the first one?
I don't know. What was the first one? Oh, gravitation. Yeah, so gravitation and the motions of orbital mechanics.
Astronomy.
Yeah, in astronomy, because realizing that
the first.
that
Oh yeah.
yeah, when an apple falls from a tree, it's the same force that's keeping the moon
the planets
orbiting. Yeah,
and the moon's orbiting.
yeah.
And the second one is this unification electromagnetism. And then what's next? Oh, theory of everything. That's right. We're still working on that, right? So
well, I mean, I don't necessarily know that that it's possible to unify everything. It's possible. People want to unify gravity with electricity and magnetism and quantum mechanics and
gravity, electromagnetism, weak interactions,
yeah.
We have talked about these before.
Yeah. So.
And hence, so standard model.
There's a standard model. And one of the
problems
problems with the standard model, and also I think we mentioned string theory before, is that there's another part. There's something else in the universe. The universe is mostly made up of dark matter, and the standard model does not include dark matter, and it didn't make a prediction about dark matter. So I see that as a big problem.
That is, I mean, it's incomplete.
If you want to have a theory about everything, then your theory, you'll form a theory that will predict everything that you're seeing, right? And then it will predict something that you don't see, and then you can go off and look for it. So they did have the Higgs boson. The Higgs boson was predicted in the 1960s, and they worked on it. They finally were able to unambiguously demonstrate that it exists. So that's a a credit to the theory, but dark matter is still out there, and string theory came around in the late 70s and early 80s with these extra dimensions that people were thinking about. And so you would think that a theory that was able to predict everything, that the string theory would predict that there would be something like dark matter, but dark matter really started to come into its own. Well, of course, in the 1930s.
Tell me about the 1930s.
What about dark matter in the 1930s?
Sure.
Well, there was an astronomer. I can't remember. I think his name was Hinkle or Zwinky, something like that.
We did talk about this.
I don't remember his name. If I see his name, I'll remember it. And he applied what's called the virial equation to some galactic clusters. So what that means is, so if you have gravity attracting things and everything is falling in free fall, so it's just like a bunch of springs that are jumping all around and everything. And so you can measure the kinetic energy from the velocities. The velocities can be measured because of the redshift of the red and blue shift of objects. So he put it all together and figured out, oh, well, we've got a whole lot more energy here than I can account for from the what appears to be present. And so and he published that. He says, look, there's more matter here than we can. And people just kind of yawned and said, well, yeah, but maybe there's dust and maybe there's a lot of dark things. And so later by the early 60s, people were also observing galaxies and showing that the rotation of galaxies was almost like
virial theorem.
Did I say I said virial theorem? Yeah,
you did. Yep.
Yeah. So that's what that's all about. And so he realized that there was something there that wasn't observed. And so that has finally, kind of developed into this big deal, meaning that most of the matter in the universe is
unknown,
is transparent. Shouldn't be black. Right. It shouldn't be dark. It really
it's not. It's not interacting with what we were talking with light, basically.
It doesn't interact through electromagnetic interactions or the other forces.
Maxwell's equations is not going to describe dark matter.
Maxwell is not. No, Maxwell.
So, all right. Now, what time is it?
It's time for your favorite subject.
What is my favorite subject?
Gosh,
I don't know.
Where to your, I don't know, shopping? I don't know.
Okay.
I think it's like, I know what it is. I'm just teasing.
Is it shopping?
It's aliens. Yeah. It's aliens. It's where to get a good haircut.
Yeah, actually, I need to figure that out. But before that, might as well, let's see here. Aliens.
Aliens.
Why not? Or UFOs. Does this thing play? We shall see what happens. And
yeah, we're still kind of coming up to speed with the technology, but people will forgive us for that. It's like
on Wednesday morning, an unidentified flying object, UFO, in the shape of a Zeppelin turned on its side was spotted floating over Roswell, New Mexico. Multiple people shared videos of the unidentified object.
I mean, look.
Some estimated the object to be anywhere from 15 to 20 feet in length, with footage showing people ducking in front of the frame, indicating it is not something that could have been done via computer-generated imaging, CGI. Some are calling it the clearest UFO footage this year. It is immediately unclear what the object is. However, some have noted how the object appears to strikingly resemble a shiny silver-colored blimp. Some have opined it could be a spy balloon similar to that seen earlier this year.
What?
Roswell is famous for a 1947 UFO incident that happened near the city, resulting in alleged government cover-ups and accounts indicating an alien ship crash in the area. Since then, Roswell has been well known for this legendary flying saucer tale. Do you think this UFO was from outer space or a man-made object?
Well, what do you think?
I don't know. I don't know. It it looks pretty compelling.
Here, let me turn on. I don't think this person is going to say anything. Yep. So look at that. I mean, that looks pretty real to me. I mean.
Yeah, I agree. I don't know. Maybe could be a helicopter.
That's not a helicopter.
Not a helicopter.
No.
Could be
Like,
a
could be,
oddly shaped balloon, but there's a
what is that? Here, let me see if the guy's saying anything. Nope, he's not saying anything. It's just music. Yeah, I don't know.
I just don't know.
So, all right. See, this might be an example of something that who knows? Who knows?
Who knows?
Like, so this was this happened on just to give you context, this was on May 17th, 2023.
Cool.
And it was spotted over Roswell, New Mexico. So some have estimated the object to be anywhere from 15 to 20 feet in length.
You notice how it's almost perfectly oriented over that power pole.
Yeah, I don't know. I mean, it's I don't think it looks like it's further in the distance though.
Oh no, now it's moved a little bit.
So, but all right, I think this videotape or video is just on repeat, showing the same few seconds of this person who took it.
Yeah.
As one can notice, there may still be some blurring technology at work here, as Leonard likes to say.
Yeah.
Even though it's broad daylight. I mean, but then again, so this is why for anybody who's actually interested, you should always carry a camera with you.
Everybody has a camera. If you have a phone, you got a camera.
Well, no, like one that can zoom in, really close.
So
like,
there's okay,
but
I mean, at least there's billions. There's more cameras on Earth than there are people.
Yes,
so
you have stated that
as I've
before,
stated
many times.
Mm-hmm. So, but I mean, I don't know, Shen. Looks pretty compelling. Like, I don't know. And then there's an airplane next to it. Like, what's up with that? Didn't the people in the airplane see it?
That looks like a turtle. That looks like a flying turtle.
A flying turtle.
Yes, that's my view. That airplane looks funny. So I don't know if that was just superimposed on there or what. But point is, who knows? I mean,
yeah.
I need to develop a collection of things that are not too absurd that could possibly be of something.
Yeah.
So,
and then what you should expect to see is some kind of unity. In other words, you should expect to find some common elements, like
what?
Like, unless we have well, I mean, it's like if there's aliens coming to the Earth,
yeah, they have different.
Then their technology should have some convergence.
Similarity?
Yeah, we should see.
Not necessarily. I mean, there's various ways to fly. For instance, like a helicopter looks vastly different than an airplane.
Okay, so we should see helicopters. We should see helicopters and airplanes.
Well, no, I'm just giving you an example of how you have different technologies that can achieve the same thing and they look different. So aliens could have different ways of flying.
But my point is that every time we look at one of these alien things, one of these UFO things, it's something. First of all, it's usually very hard to make out anything, and there doesn't seem to be anything common to it. It's nothing at all common. It's always something. It's three lights together, at night, or it's things that are tumbling. You get my point.
Right. I get your point.
Yes.
And I recall our many conversations on your particular theories about how strange that we exist in the first place.
So, it is strange that we exist. People say that the universe is fine-tuned for life to exist, but I'm not so sure that's true. I think maybe it's just
we're an odd fluke.
Yeah.
Yep. So you being able to talk about it is weird. All right. So we're gonna have to cut this short, or rather, we've already been going so long. So
we've gone about 15 minutes over our usual.
That's what always happens. The normal time now seems to be whenever you finish talking, or
whenever I finish talking.
Whenever I finish talking. Okay. Maybe I should just put it on my
I thought I really enjoyed talking about Maxwell equations.
Yeah,
I don't know. I don't know why. I just think it's, when I sit back and think about it, it's like, wow. I mean, it's cool. But,
yeah, I mean,
you know.
if you can, even if you don't completely understand the math, I mean, just being able to understand conceptually how you can
Just conceptually,
relate
yeah.
electricity and magnetism and how you can use that to derive like a fundamental thing like light.
Like the speed of light. Yeah.
Exactly. In fact, describing actually how light would move, right? And what creates it, so to speak, what light actually is.
Yeah.
Right. From a classical perspective, at least. All right. Look up because you never know what you will see. See you all next week. Remember, support the show, patreon.com/SG2 on space. And thank you once again, Kyle Baker, Sam Welsh, Tim Brown. And if you guys have not noticed, we also have once again, podcasters.spotify.com.
Spotify, boy, things are going to start happening now.
Yep. So I will put this episode, if you're listening to this on Spotify, then this was originally premiered on June 6th, 2023. Typically, the live episodes are on YouTube. And of course, you can catch it at 6:30 p.m. U.S. Central Time, typically on a Tuesday.
We target Tuesday. Sometimes we don't make it.
Yeah. God. Well, I knew that was happening. All right. With that, thank you, everybody.
Good night.